So, welcome to second part of today's lecture, which is going to be on security and privacy in the Internet of Things. Um, so, in general, we are going to be talking about not just what security and privacy are. We will also be talking about what are the general best practices. What are the good things that you really should be doing if you are ever in charge of or are even a user of these IoT devices? I'm sure a lot of you already have some IoT devices at home, and maybe some of these things might make you very, very afraid of the current systems and might make you question whether or not they are actually secure. I'm sure you've read a lot of very scary articles, but these slides will contain also some examples of bad practices. But in general, you shouldn't be very afraid of devices unless you really don't know anything about them. But these slides hopefully also give you some insight on how you can help secure yourself from some problems, at least whatever is within your power. And if you are a computer science student and might be in the future in charge of developing some IoT systems, then these are some things that you should really keep in mind. So, talking about the most common general security issues that we have with IoT systems, the first being something that's quite common, not just IoT systems, but also in general, anything to do with the web, which is improper input validation and representation. So there used to be this thing called SQL injections back in the day when I used to do some code in PHP for some websites. Um, you always have to make sure that when a person is putting something in a form on a website, you have to make sure that they don't put weird SQL queries in there. So for mining students, you don't have to worry about understanding how this works. But for computer science students, you need to know that something like this can basically give the user all the user data, basically. So this used to be a big problem back in the day, and you needed to do validation on the client side and the server side, and making sure, let's say, from using regular expressions, that what you actually have in the form is really um, a email address and not something else. So basically only allow list things. So what do you only allow to be in certain fields? And don't put stuff like deny list. Don't say that, yeah, I take everything except XYZ. You should rather say I only accept X, Y, and Z in these forms. So allow listing things. So on the other hand, even though you do some input validation, it's important to do this also on the server side. So even though you're doing it, let's say on the front end, or let's say on the user end of an IoT device, you also need to do the same validation and all of these steps on the server's end, because a lot of attackers like to use scripts or bots to use whatever the underlying protocol is between your devices or IoT devices and servers to send weird requests and try to abuse. These can be SQL injections, that's the canonical reason people try to do, and also buffer overflow attacks, which basically try to send so much data or make the server use so much data that it ends up crashing the server, and sometimes also exposing some data from the memory that causes memory leaks as well. So you need to be careful. And again, make sure you have allow listing and not deny listing, and rate limiting. So don't let people just send a million gigabytes of data per second to your server. Make sure that if this is just a data application that requires only a few kilobytes every minute, then make sure that you're limiting how much data someone can send from any particular device. So a lot of different projects that you might see really assume that if you just use the standard SSL TLS encryption, which is basically the thing on your browser that says you have a lock on the top left usually, that just means that everything is fine. So just encrypt everything and be done with it. That is generally not the case. Um, just encrypting things doesn't mean that you are secure from all types of attacks, especially because the type of encryption and also where your encryption is happening. So, for example, in browsers, the encryption is happening on your browsers, and but the only things that are being encrypted are the actual request bodies, but not actually the path of the request. And your internet provider still knows what websites you're visiting. So that stuff isn't really encrypted. So you really need to know what is being encrypted. Another way where people miss security features is by just closing everything off and saying, yeah, so my software is proprietary. People do not know how my code works, so it should be really secure. So this is obviously something that Microsoft does, Adobe, all of the big software companies love to do this and love to always say that, yeah, our stuff is proprietary, so it adds a level of security. Um, the reality is that the more popular something is, the more likely it is that people are going to find vulnerabilities in them. So just because your security is obscure or your product is obscure doesn't mean that you're automatically secure. I'm sure all of you are aware of various different types of vulnerabilities happening in all proprietary softwares, including IoT devices like your smartwatches getting hacked. Happens all the time, even though they are proprietary. Um, so just because you have proprietary code that people cannot take a look at doesn't mean that you are automatically secure from all problems. So on the other hand, so you have proprietary software and then you have free and open source software, so-called FOSS software, which in which case you publish the source code on a public platform like GitHub, like we do our lectures. So just because so the people in the FOSS community also like to say on the other end, okay, so our code is publicly available, so a lot of security researchers are probably looking at it and publishing problems and then fixing them. So this is to a certain extent very true. Let's say the most popular FOSS project, the Linux kernel, is probably one of the most exposed public pieces of open source software in the world, which is widely also used by everybody. Um, Whether you're using an Android phone or using, let's say, my PC also runs a Linux kernel, um, has vulnerabilities happening every single day that are reported and then fixed by people. So just because, so a lot of GitHub repositories do not bother with very advanced security features or penetration testing because some of them just will claim that, okay, we are free and open source, and they do not really invest in the security that they really should be doing because they're relying on the open source community to come in and then report problems with it. You really shouldn't be waiting for this. You need to be proactive always, no matter if you're proprietary or free and open source, and always make sure that you're patching your vulnerabilities and looking for vulnerabilities where you might have them. So the mitigation in general for missing security features, prepare for the worst possible outcomes and don't hope for always the best possible outcomes. And knowing where you are, your software is most vulnerable is very good, so you can then fix that. And also maybe let your users know if you find a vulnerability that is a problem, and let them know that, okay, they need to update their software, push security fixes. Sometimes you have to force an update for anything to work. That's probably a very good thing. Yeah. Another type of common attack is playing with time and state. So in general, when you are a programmer and you try to build some kind of a system which is expecting data in a certain order, you can't really rely that the person or the attacker is also going to send you data in the same form. So if you have semi-interlinked data forms that, let's say, one collects some user data, some collect credit card data, or some of them have something else, um, if you do not enforce that the user does them in a particular order, not just on the client end, but also on the server end, you should really expect that some attackers are going to try to do things in different orders, like change the credit card information after they create the account, even though you don't expect that they can do that, but that API request is still valid. So you need to really lock down the order of how your control flow is going into. So don't assume that your control flow is always synchronous. Be aware of parallel threads if you're doing things in parallel on the server end and even the client end, especially during inside of multi-processor systems where there are different processors that are processing different things at different times, and also distributed computing when you have different computers on distributed locations computing different things at different times. You need to really make sure that asynchronous events can occur, and it should always be expected, in fact. And you should really enforce, if you really expect a certain order of things to happen, to enforce this type of control flow and not allow other types of requests in other orders. Error handling is also something that does happen. It's basically TMI. So you might sometimes go to a website, do something, and you see some lot of weird errors that you don't really know what happens. So I think from CodeCalc, a lot of you encountered some errors where it wasn't able to copy the files from lecture 4, sorry, exercise 4. And this was, you see a command line argument that is being shown in the error message, which is basically this command rsync, which is used to copy the exercise folder into a solution folder, wasn't able um, to see that there is an ampersand in the name of the exercise, and did not really say that, okay, this is the reason why we don't accept this solution. Instead, it just gives you a random error, and then your exercise is in a weird location, and you have to do all of this. So the error handling for COCAC seemingly isn't really as exhaustive as it really should be. Somehow I was able to figure out that, okay, this is the reason why it's happening, so we know how to not do this in the future. But really, there should be a debug mode that just says, yeah, we had an error, please try again. And they really shouldn't be part of production systems. I'm not claiming that CoCalc is insecure, it's just an example. But in general, you always need to have a debug mode that you only expose to your developers and administrators and not to your end users. And in general, just code better. A lot of things with security. So security is a part of having a reliable user experience. So if your user is looking at your piece of software as very unreliable, they can try to look around to do the same thing without going through the correct processes, and these can also reveal attack vectors to attackers. Um, Basically, if so CoCalc, for example, has this ampersand problem. So an attacker could just, let's say, make sure that there is an ampersand in a publicly accessible project on CoCalc, and now every single person who's visiting CoCalc now has a weird error happening on their website. I think back in the day, there were also certain blogs where if you could just put in some CSS code in there, and then everyone's screen who visited that website would suddenly have this weird new CSS rules. So the mitigation in this case is on the programmer's end. You kind of just have to make sure that you are having very good, rigorous code or coding standards, and making sure that your code is reliable as possible, having test cases that test pretty much every type of different user interaction that you can think of. And this makes your thing more secure because it is more reliable as well. So now moving on to the general aspects of privacy. And before we do that, we need to kind of talk about the differences between what privacy is and what security is, because these are two terms that we generally talk about kind of in the same breath often. So generally speaking, privacy is the control and proper usage of data. And sometimes you're more specifically talking about user data. And the key in privacy generally is consent from the user who owns that data. And to go into even more detail, it's informed consent. So your user need to be informed to what they're giving consent to. So what the data is going to be used for, who's going to use this data, how long this data is going to be staying, and where it's going to be staying, and what can I do to delete this data if I don't want to um, store this data anymore. In other words, how do I revoke my consent retroactively? And security, on the other hand, is protection from unauthorized access. So it's the other hand of having a secure system. So you need to really have both of them to make sure that your systems are as secure as humanly possible. Um, and in general, they're not equal terms. And privacy is also not a subset of security. So just because your system is completely secure, that isn't the end of the story. So just because you implemented all possible you prevented all sorts of attack vectors from any type of attacker doesn't make sure that your software product or hardware product or IoT product is completely private for your end users, and doesn't mean that you're adhering to all the privacy respecting principles. So you really need to take care of it. But on the other hand, so the other ways is true. So security is a prerequisite for having privacy. It isn't everything, but you cannot have a private system if your system isn't secure. This is quite obvious because let's say your system isn't really secure, has a lot of user data, so your data gets breached, and suddenly your user data is not private. Doesn't mean that automatically security ensures privacy, but it means that having security is a prerequisite for it. Without security, you cannot really ensure essential user privacy. So now we go into some general privacy issues and the best practices to how we can mitigate them. These are four very general ones. There are obviously many of them, including there are many others for security, which we haven't mentioned before. So um, these are the most notable ones that we're going to talk about here. So the first one, identification. So a lot of the time you have software systems where you have to upload or use personally identified information, and this needs to be always available. So let's say you are an IoT system where you are monitoring health data from a person because this person has as let's say some kind of a critical component that tracks their health. Let's say it's their heart rate, their blood pressure, or something like this, maybe insulin levels, because these insulin pumps sometimes which are automatically pumping insulin. Generally, these systems have critical medical data which can be personally identifiable, let's say blood groups, some other information. You really need to make sure when you have this information that you're limiting how much data you're collecting, number one, and then restricting how you're using this data, especially also how long you're retaining this data for. So if you don't need this data for more than 10 seconds, you're processing something and then you don't need this data anymore, make sure you're deleting it afterwards permanently. And then disclose if you're keeping the data somewhere, and disclose how long you're keeping your data, and disclose also where you're keeping this data and how a person can then retroactively revoke consent and then get this data removed. So localization and tracking is also something that goes with identification. So if you're identifiable inside of your system and your location data is being used for some product, then this product can determine not just recording of your location at any particular time, but also across space. So you know not just where a person is at a particular time, but also where they have been for the last 20 days or 30 days. I mean, a lot of you might have this tracking feature from Google where you can share your live location with your friends. And generally for this, you have to have these location services always turned on your phones. And they are just generally turned on, and do you really know which application has collected what data, where it stored it, and whether it really stored this data permanently or whether it used it only for a second for doing some notification that you're close to another person, or did it delete it afterwards? So essentially, tracking is a huge problem that goes hand in hand with identification, and this is a huge problem with similar mitigation strategies like before. And in addition to this, you also can sometimes use inaccurate location data. I think we all have these options in our phones to use inaccurate localization. So let's say maybe within the city or something where you are, but may not be the pinpoint GPS location of where you are, and you only use the pinpoint location when it's absolutely necessary to do so. And then you have additional measures to mitigate any privacy issues coming with that. So profiling is something that is completely different and something that a lot of you may not be actually aware of, because the first two is something that I'm sure a lot of you already know. So profiling is basically when you compile a lot of data about users that is not actually identifiable to people. So you're not collecting their name, you're not collecting their date of birth, you're collecting seemingly unrelated data that could apply to a lot of people about a lot of users. And then basically you use machine learning clustering techniques then that just basically allow you to tell, okay, even though this person is seemingly anonymous, they're using a very similar browser, they're using a very similar version of a particular browser, they're using the exact same screen resolution and DPI that another person has used, and they are using the same service at exactly the same time. These are probably the same people using the same service. And this is basically called profiling, where you correlate different types of data with different sources and create profiles of people, sometimes even without telling them. If you look into the Nutzungsbedingungen of all the data or GDPR stuff that you do when you accept all the cookies on websites, profiling is one of the things that really happens all the time. So if you go to a website, I think it's called profiling.com or something like this. I probably share that later. It basically can allow you to go to this website. You can go to this website from private browsing. You can go from different browsers. And even though you're doing this from different locations, you still can see that you are being tracked across different devices and different sessions and different times. So these can lead to a lot of privacy violations and generally they use this to sell you ads, and sometimes also price discrimination. If this person is really desperate to buy something, maybe they will increase the price. This happens, let's say, in search pricing for Uber, but not exactly from profiling. And also social engineering attacks, which are an additional attack vector for security. To mitigate this, in addition to all the different mitigation strategies for privacy that we've talked about, you additionally need to have transparency. So all stakeholders, mostly the users, need to know how your information is being managed and in accordance to what commitments and objectives. So if a website is doing profiling, then they really need to state that they're doing so. And sometimes it's very hard to figure out unless you read 30 pages of privacy documents to do so. So it isn't that great right now for profiling. So all of us probably are being profiled if you're using modern browsers with JavaScript enabled. So unfortunately, this is some of the hardest things that you can prevent yourself from doing, from getting profiled from. Lifecycle transitions is something that you could say is particular to IoT devices also, but also some user devices, especially when you, let's say you're buying a new one and you want to sell the old one to someone else on eBay. And when you sell this, usually you can log out of your device or out of this device when you sell it to someone else, but that doesn't really mean that the data inside the device has been completely deleted. So you need to make sure that when a transition occurs in the life cycle of any device, it can also be a general phone or anything else, that you're really wiping everything. Like do the factory reset when you really want to sell something to someone else. A lot of the times, I remember once I currently have a projector in my room that when I purchased it from MediaMarkt, it wasn't advertised as a used product, but it turns out that it was a used product and someone else's Google account was already on it. So obviously very horrible to see that happening, and make sure that when you have these IoT devices which are connected to the internet, where you put your accounts, sometimes your credit card information, your financial information, that you really have strict authentication protocols. So make sure you always have to log in if you're always storing this data. And remember to make sure that you're not retaining this data more than necessary within the life cycle of using this product. So those were some good examples of what you really should be doing. And now we're going to talk about some really notably bad examples from history of when security and privacy was really, really not well taken care of. So this is a paper from quite a long time ago, from 2012, where they tried to look in to the general IoT systems that are in smart home systems, and they were able to figure out the bathroom habits of people inside of a working environment just by looking at sensors and not even reading sensor data. So how did this actually work? So Benjamin already talked about PIR sensors. So these are the sensors that detect when people are walking through different regions. These are generally used by, let's say, automatic lighting, automatic locking of systems, so on and so forth. We already know how this works. And in this example, this is a workspace in which there are a lot of these small PIR sensors that basically know when a person walks past it. And as you can see here, there are a lot of them are inside of some rooms for automatic lighting. A lot of them are in the hallways to turn on the lights automatically. And turns out they're also inside of the bathrooms. Like, you know that these sensors also work for when you flush. Sometimes the flushers automatically flush the toilet once you step away from it sometimes, especially in the men's room. I'm not sure how it works in the women's room. But definitely these sensors exist there. And what they basically did is they didn't really have to even look at the actual data being transmitted by the sensors. What actually happened is whenever any kind of data is being transmitted from any of these sensors, there is an electromagnetic pulse that occurs. So if you're aware of Faraday's law, it's basically when there's a change in electricity inside of, let's say, a coil of wire, there is a change in the electromagnetic field that is associated with this. So basically you can detect whenever a sensor is sensing anything. So let's say you sense this sensor over here goes off. And let me use the pencil. Let's say this sensor here goes off, and then in a second later, this sensor, and then this sensor goes off, and then this sensor goes off. You can then know that the person that was sitting in this seat went to the bathroom and then used one of these bathrooms. And then what they detected with this is this is just information. This is not knowledge, right? What they also were able to do is that a person did not come back to the place to wash their hands and did not basically leave enough time between triggering this sensor and this sensor while going back. Let's say it was only 1 second between triggering this sensor and this sensor. It basically means this person did not wash their hands. But on the other hand, if let's say this sensor was triggered and then 20 seconds later, this person comes out and then triggers this sensor, then you basically know that this person washed their hands because they were there next to the sink for 20 seconds, so they're likely to have washed their hands. So that's kind of really scary, isn't it? So collection of certain data might reveal very interesting and unexpected information which you never really intended to have. So you really need to implement some kind of security where you are protecting data both from encryption and authentication, number one, and then also protecting this data accordingly. So from the software layer, obviously you collect, store, and analyze data according to the GDPR and be compliant with it, but also making sure that when you are securing the data in transit, let's say from electromagnetic pulses, you are shielding your cables from being able to be analyzed by other sensors. Another more recent thing, which is kind of scary. So previously in previous lectures, we used to have this idea from 2015 where the Jeep Cherokee was this car where attackers were able to take control of the whole system and basically do very, very bad things. And somehow, 10 years later, this is still a problem. And the place where this really comes from is vulnerabilities in the infotainment system. So these things have Bluetooth capabilities. You know that you generally have Apple CarPlay and Google, I don't know what it is called these days. and basically left this car particularly for something called privilege escalation, where instead of treating the incoming requests as a request from the person operating just the Bluetooth system, it basically gave them administrative rights and allowed them to control basically a lot of the things inside of the system, like the doors, the wipers, the lights, a horn, like pretty much every electrical system that is electronically controlled from your infotainment system was basically hijacked by the attackers completely remotely. Because turns out our modern cars really have these nice 5G modems on them, because you like to have like a lot of different things like satellite connections for GPS. You want to have up-to-date maps, up-to-date firmware, so they are always connected to the internet, um, being accessed by hackers sometimes also. And the most horrible thing is that they could also connect to the steering wheel and operate the steering wheel. Um, Back in the day, this wasn't possible because steering wheels were always physically connected to the actual wheels. But nowadays, in addition to the power steering, we also have the so-called steer-by-wire system, which is similar to how how functions in an airplane works, because there is no longer a physical connection between the pilot in the airplane with the yoke and the actual flaps, because it takes a lot of energy to move these giant flaps in an airplane. Similar things with the steering wheel. When our cars are heavier and heavier and you want to have more precise control of the wheel, nowadays we have sometimes electronic control of the steering wheel. And in this case, because it wasn't a physical connection, there's a motor also connecting, and that can control when the steering wheel is moving in each direction. This particular car is also vulnerable to this problem. I think the Cybertruck also has not just steer by wire, but also brake and accelerate by wire, which means that there is no longer a physical connection between the gas pedal and the actual the motors that are actually driving the vehicle. And this is probably becoming more and more common, especially with electric vehicles. And you could even only think about the vulnerabilities that you can have. You basically have a remote control car, like a tiny car that we used to play back in the day with these tiny controllers, is what you have with big 5,000 kilogram vehicles that are driving on the Autobahn at 200 kilometers an hour. And basically just taking over these things is really not good. So just a tiny Bluetooth component that really caused or can cause really, really horrible things, which you really only see in these wacky hacking commercials or hacking scenes in movies. And if you want to guess what the reply from Nissan was after this was discovered and they asked for comment, they declined to disclose any specific countermeasures or details for security reasons. So once they patched this problem, they declined to say how they patched it and how they are preventing this from happening in the future, because they want to say, yeah, for the safety and peace of mind of the customers, we do this all the time, but we also don't want to tell people how we're doing this. So this goes back to, again, security through obscurity and how this is a giant problem. And in this case, because Nissan was like, yeah, our systems are secure because no one knows how our software works, this wasn't obviously enough. And hopefully the new models of these cars were recalled and then made sure that they were secure again. I don't know if this is really still a problem or not, but yes, huge problem. So we talked generally about security so far and privacy as well. And now we're going to talk about specifically security and privacy relating to IoT, because this lecture is about IoT, security and privacy. We have some tables here which have this taxonomy of different attacks that are possible with IoT devices and also particular solutions that you can use. These are kind of general sometimes when it comes to especially cloud IoT systems, but sometimes you need to have more specific solutions that are not possible and are not really the same in terms of cloud security. A thing to note here, the tables here are basically screenshots from this research paper. And when we publish this on GitHub later today, we will recreate these tables so that they look better, because some of them are really small. and make them easier to read for you. You don't really need to know the details of the different types of protocols that are really used, especially all of these here. In fact, even I do not know the details and how these actually work. But generally, knowing what type of attacks are and the general types of solutions that you can use is kind of relevant for the examination. So, starting with the perception layer. So in IoT, you have the layer which perceives data, like your sensors and other nodes. So firstly, this is the RFID things. So sensors are very different in the sense that sensors are looking for very specific types of information and then transmitting this information. So RFID nodes are on the other side, which don't really need power to really perform. These are just these things, for example, inside of grocery stores or some fashion stores where they have these tags that are RFID, where if you go through, let's say, the door, then you can track whether or not this particular item is being taken out or um, into the place. So it doesn't really need power to be to operate. So you can just have this tracker on yourself for 100 years, and it can always be used to track you. Not just this, you can also be doing something known as a denial of service attack, which basically means the radio frequencies that these things use are flooded with random stuff, and basically you then cannot use these RFID tags anymore. You can also do spoofing, very common with RFID tags. I personally entered the university with these ID tags. So these tags, if they are not secured with access control and data encryption, can be spoofed. And basically you can make 1 million copies of these different tags and then use them as much as you like. In our case, these are secured basically based on access control. So every tag is particularly tied to a particular person, and there isn't really any way to copy them in a way that you can use them again. So no replication. And also making sure that there is a non-linear key algorithm used. So we will go into specifically the type of key algorithms used for cryptography when it comes to very small IoT nodes. But yes, moving on to sensor nodes. So apart from RFID nodes, what you can do is just subvert your sensor from working, because these sensors always have some kind of electronic authentication methods. These are very easily subverted. You can also cause particular sensor nodes from failing by basically just putting a particular magnetic field that prevents a sensor from functioning if it uses magnetic fields, which kind of goes into the denial of service aspect as well. And you can also affect stuff like privacy. Like I said before, the sensors with the PIR, where you were able to see just by the magnetic effect that the sensor is sending some data. So basically, you need to also have some protection against passive information gathering and implement basically authentication of which nodes can access data from your sensors and also how private this data is. And making sure that you are not just taking physical methods, such as shielding the sensor from physical tampering, but also from authentication and programmatic approaches where you have authentication methods and making sure only a particular control node is having access to the sensor data. Now talking about the network layer, so Benjamin talked a lot about communication protocols. So pretty much every communication protocols, especially wireless communication protocols, are susceptible to tracking, eavesdropping, denial of service attacks, and a lot of different things. Basically, there are a lot of different methods that you do to taking care of all of these things. So depending on the mobile communication platform, there are different types of mitigation approaches. And depending on the type of infrastructure, so for example, in your Wi-Fi protocols, you have different types of security. So you may be familiar with WPA2, WPA2 Enterprise, and the newer WPA3 system. The older WPA2 systems basically do this handshake at the very beginning where you have your Wi-Fi password, and based on the Wi-Fi password, there is this key exchange that happens. And during this key exchange, it is possible to basically eavesdrop on this handshake that is happening, and then pretend like you're doing this handshake like a million times, and then you can eventually figure out what the password is. So, in my experience, you generally have only about as little as a few seconds, going on to 8 hours, depending on the type of router. You can basically just figure out the password from the WPA2 system. But the modern WPA3 systems, not only do you have a password, but also with every system, there is a pre-shared key that basically is transferred only once. So you really cannot, the eavesdropping approach is much more insignificant because the actual thing that you have to eavesdrop on only happens literally once, and then every other time that you use this Wi-Fi network, you're not really using unencrypted data packets. So going on to the other part of the network layer, which is cloud computing. This is very similar to the other security approaches that we talked about before. So identity management, making sure that only particular people have access to data, and also authentic nodes which are communicating with your cloud platform are handling the data which are protected. So having particular data access controls. Also, for example, we talked about a lot of different things like location privacy and identity privacy, and also being kind of aware of your nodes because they're in other physical locations and are more susceptible to be attacked than, let's say, your cloud system, which is in a data server very far away. Basically making sure to figure out how you can figure out that your nodes are compromised. So making sure that your private keys are not stored in plain text, and maybe it is impossible to get the private keys out of your nodes without sending a signal to the cloud server that it has been compromised. I'm pretty sure most laptops and phones these days have intrusion detection systems in which this is also the same reason when you change sometimes a camera from your laptop or your phone or even even your car. Sometimes if you want to change a very specific sensor, you have to go back to the factory sometimes and have a very specific reprogramming of the central computer, because now it has to basically recognize the new signature of the new sensor that you're being using in your new system. So there are many different things that you could use to prevent these types of attacks on your nodes, to prevent your entire cloud system from being attacked. And when it comes to the application layer, obviously there are many different application layer protocols. So this basically pertains to the specific application you have. So many different cloud platforms can have many different IoT applications hosted on them, and many different protocols are used for different types of IoT systems. So every single application needs to have its own layer of security. So on every layer, going from the sensor to the cloud, the network, and also the actual application that are running on this whole stack have to be really secured from any type of problems. And depending on the type of protocol the application is using to communicate, not just with the sensors, they can be using HTTPS, they could be using TLS. You're using different types of communication protocols and also encryption and privacy protection protocols to protect both privacy and also security inside of your IoT system. We're going to make a short detour into edge computing. We have a whole more in detail account of what edge computing is in a future lecture, particularly lecture 8. But for the purposes of security and privacy, we're going to talk a little bit about edge computing. So in IoT systems, because your IoT devices are generally really tiny, like your smartwatch has some amount of processing capabilities, but sometimes it really has to depend on your phone for a lot of operation. This is kind of the idea when it comes to edge and edge IoT. So basically, you have an edge system which is operating and like doing the complex data validation for a lot of tinier IoT devices which can only do very simple data validation. And this is something that sits between your independent IoT devices, which have generally one or two common edge devices that are doing more data processing, and sits between the cloud, which basically does the most complex data validation and has more analytics. And sometimes the edge can store some data which you really need all the time, and the cloud stores basically all data from all the time. And you really need to have different types of security pertaining to edge and fog devices compared to the cloud, because they have different power and processing needs or requirements. So they generally are not as powerful as giant supercomputers on your cloud. So you really cannot use like a lot of more complicated techniques that take a lot of processing power to secure them. So you are taking a compromise, but still using different techniques to ensure that you are having privacy preservation and also security preservation in edge devices. And we're going to talk a little bit about how to do this now. So there was this paper which has a survey on different edge computing based designs for IoT security. And these slides here are based on this. So there are generally three parts of having security in your edge systems. You have the user-centric approach, the device-centric approach, and then you have like an end-to-end security coming from your IoT devices to your edge devices and then your final cloud systems. The first part, so one thing that is common in not just edge systems, but also any type of security system, is that the users are the most weakest link in this architecture. And this is especially true with IoT edge architectures, because as you can see here, you have the edge where there's a lot of tiny devices here that have some processing capability. There's a phone, maybe a tiny Raspberry Pi, a tiny PC, another Raspberry Pi, maybe your actual car has some IoT, and it's connected in the end to some end devices, like let's say some thermometers, some smart lights, your GPS infotainment system in your car, maybe a tire pressure sensor, and let's say other sensors like your smartwatch. And in the end, all of these have to go through your user, because the user has a user interface that connects them to the edge devices. Excuse me, I had to cough there. And the user also has an interface to the cloud. So if the user is not aware of how to protect themselves, both from the aspects of security and privacy, your whole system is vulnerable to attacks. So there is the user-centric approach to edge-based security architecture, in which you have to first make sure that the user is aware of how to protect their data. On the other side, you also have the device-centric approach. So low-powered IoT devices, your tiny sensors here, and also the edge devices cannot really use the same security protocols that the cloud uses, because like I said, they don't have the same power and processing power and also electrical power that the cloud has. And depending on your application, smart home, smart transportation, smart health, you want to offload some of that data to the cloud. And during this process, you really need to have some kind of security, like for example, having a secure device profile for every single edge device and every single IoT device, both on the edge and also on the cloud. And having secure keys that are present on your edge devices, your IoT edge devices, and also on the cloud, making sure that you're always talking to the device that you're intending to talk into and not another device that is pretending to be the other device. So you have a different set of protocols to do this. A tiny detour to cryptographic protocols. You don't need to understand the details of how these work. But in general, the RSA protocol, which is one of the first asymmetric encryption methods, is kind of a bit too heavy for low power devices like edge devices or as well as tiny IoT devices. You can also use elliptic key cryptography. So you can turn some RSA keys. You can do RSA using elliptic key cryptography, and it can be acceptable but still slow. Maybe you can use this on the edge device but not on your IoT device. In this case, you have to do also symmetric cryptography, which basically means it's like a password, and that password is being used by both the IoT devices and also the edge and server and cloud servers to making sure that the data is encrypted. So the most common one is generally AES 128-bit, which can perform well even on tiny 8-bit microcontrollers. So your tiny Arduinos and your tiny MCUs can also do this very, very nice symmetric cryptographic approach. And very often you have specifically cryptographic processors on your tiny IoT systems, because you want to make sure that the private symmetric keys which are stored on your IoT devices are not copied by external actors. So even if you have some protected access to your unprotected access to your tiny IoT devices, it basically means that your cryptographic keys can be copied. A very fun fact, basically any credit card or debit card that has this tiny chip in it, or your SIM cards in that case, also have a tiny computer inside of them that do very, very, very simple symmetric cryptography. So they don't have batteries inside of them. So your credit card doesn't have any battery, your SIM card doesn't have any battery, but whenever your phone needs to identify yourself to your, let's say, your cell provider, or your credit card company wants to identify that it is indeed you using your credit card, generally what happens is this PIN that you have is a password that unlocks the encrypted key that's on inside of your debit card or your SIM card PIN. So whenever you have a PIN for your credit card or your debit card, it basically means that there is a cryptographic key that is not accessible unless you enter a particular key, and then your tiny little device, in case of your credit card or your SIM card, can do this decryption, and then whatever it needs to say, it can do. That was a tiny detour where you need to have different types of encryption protocols. Here is some comparison of the size of message that it can encrypt and the amount of time it takes for different protocols to encrypt or decrypt these data packets. And in general, there are some of them which are very, very time efficient, and some of them are not. So depending on the type of computation power you have on your device, you have to choose a different protocol for not just hashing, for doing HMAC authentication, but also for encryption and decryption. Coming back to IoT edge security, you also have this concept of distributed security. So because you might have multiple edge devices, so your edge device inside of your home could be your car, your phone, your router. These can be the edge devices, and the end IoT devices are, let's say, your smartwatch, your various sensors, your alarms, your different thermal sensors. And basically, you have a distributed edge firewall on every single edge device. So your phone has a firewall on it, your router has a firewall on it, and you cannot use the same types of firewalls on your tiny IoT devices because they really do not have the capability to have intrinsic network policies on all of them. So your tiny IoT devices cannot really detect all of the incoming and outgoing traffic. And also they cannot do dynamic rules. So let's say someone tried to do a DDoS attack on your, let's say, your thermal sensor. So your edge device is going to detect this and create a firewall rule that prevents this particular attacker let's say with their IP address or maybe their MAC address, depending on the type of network you're using, and prevents them from accessing this sensor. If you had only implemented this firewall rule on this sensor, it still allows this attacker to attack all of your other sensors here. But if you have a distributed firewall for all of your edge devices, that basically means that your phone can tell your router that, okay, I detected this infringement upon this particular sensor from this particular attacker. Please also block this attacker with this MAC address or this IP address from all of the other sensors that you know of. So you're distributing the firewall rules across all of your edge devices to protect all of your sensor devices, which may not be connected to every single edge device. Similar to intrusion detection, exactly the same type of thing that happens. So you have a distributed monitoring system for all of the network traffic that comes to your edge. So doesn't matter which edge device detects an intrusion into your system, doesn't matter if it's a denial of service attack, someone trying to use a wrong password. It will be a collaborative method in which all of your different edge devices talk to each other and have a network controller that then decides which IoT device is being intruded, and maybe it will decide to cordon off a particular IoT device from the rest of the network, depending on whether or not it's been intruded or not, or whether or not you have detected this intrusion. So firewall rules that are more preemptive, but also when you detect a different attack. Let's say there is a new rule, or let's say you figure out that there has been an attack on this type of sensor, but not inside of your network, but you figure out that there's an RFC code for this. Then you can basically push a new update on your edge that makes sure that these IoT devices are not used until their firmware is updated. And this is something that you can do more dynamically with edge networks. That was just security. And now we also talk a little bit about privacy preserving in IoT applications, and also specifically to edge devices. So this particular thing here that we're talking about here also applies to general IoT applications, but also to edge applications. And there are a lot of different ways that you can protect privacy in your IoT applications. One way is to aggregate data. So let's say you're collecting temperature data, or let's say you're collecting heart rate data from a person. Depending on your application, you may not have to give them the timestamps of when this data was collected, for example. You can just randomize the order in which you collect this data and then send them, aggregate them, and then send them at a later time to your cloud when you want to process this data separately, or to your edge, depending on your application. This kind of aggregation can kind of protect privacy, so you don't know exactly, so the processor of the data doesn't know exactly what your heart rate was at any particular time, but they still can do, like, let's say how many calories you spent, let's say from your heart rate here and your heart rate there. Like, it doesn't need to know exact details. There's also this concept called k-anonymity, which basically, when you have multiple users of smartwatches, for example, let's say you have 100 million users for this particular company that are then sending data through your phone to the edge and then to the cloud. You don't really, you basically can have pseudo anonymity for your data. So you not just make your data anonymous, because you need some kind of way to make sure that every person is getting their health data, but also the data set that is collected inside of the cloud cannot distinguish from at least k-1 individuals. So any particular data point on the server cannot be really correlated with at least k-1 individuals. So this is kind of a way to ensure that even if some data is leaked on the server, or let's say you have a malicious person in charge in the company which really likes to use your data for advertisement purposes, if you have k-anonymity regulations on the edge end, so on your end, before you send the data to the cloud, you can ensure that there is some kind of privacy that is ensured. On the other end, you can also have some more different things like differential privacy, where you basically use some mathematically rigorous framework for releasing statistical information about data sets while protecting the privacy of individual subjects. So, um, you can sometimes use slightly modified data of people. So, for example, for heart rate data, you may not always give exactly the same result that you see from the sensor, because the same response can be valid for different sensor values. And you use statistical techniques to ensure that you have privacy preserved, even though this data might be readable by somebody. So a person who can read this data may not be able to know which individual this data belongs to, because a lot of people have the same data. So this also prevents the so-called profiling approach. So a lot of people can have a similar heart rate, but tiny differences in the heart rate can also be used to identify which person this data belongs to, even though you don't store the name of the person with the identifying user ID. Also, you can use something like homomorphic encryption. I haven't mentioned this in the slide. This is something that I know of, where basically you encrypt the data in a way that the server can process the data without even seeing the data. This is something that's quite complicated that we're not going to go into, but essentially it's kind of like being able to close your eyes and still work on the data without even reading the data in the first place. It's kind of cool that you can only do with homomorphic encryption techniques like RSA, which has its downsides, like we said, that IoT devices are really hard with using RSA because they don't have the processing power to always encrypt that data. But it's good to know it's possible, and there are a lot of different ways that you can also ensure that this can happen on the edge end. Two, a final summary of what we described and what we already talked about today. Obviously, privacy and security is quite complex, and in general, it's already a quite complex topic. There are so many different attack vectors. We talked about so many different bad examples of people doing this, but particularly, we also talked about how IoT privacy and security can be mitigated. And also edge architectures is something that we went into. We now know that the relation between security and privacy is very complicated. Like security is a prerequisite for privacy, but just because you have security doesn't mean that you're automatically private. We went through some of the very best practices that you can do when you have to secure data. So as a computer scientist, you can know what I should be doing when I'm coding a new system or I'm part of a project that is collecting user data, and how to protect their privacy and how to secure unrestricted access from them. And we have some examples where you please make sure that your new cars, that I know a lot of people from computer science go on to work with Volkswagen and other companies, and there are still a lot of bad practices that happen from um, this end of the spectrum. So please, hopefully we have scared you enough that you are making sure to not do these blunders in the future. And we also talked about how securing the IoT cloud architecture and the communication protocols is sometimes a bit different from securing both the IoT devices and also edge IoT devices. There's actually, since we had two lectures today, so we had IoT communication and we also had IoT security. The IoT security exercise and the IoT processing exercise will all be having different deadlines, but for this week we have first IoT processing. So we're going to be continuing with the data we had from exercise 5, where we had a lot of data from different weather sources about weather information and also some sensors. And now we have like an average data set that we have an idea of what the average weather is going to be like for the next, so like 1 week or so. And now we're going to use this to predict energy output. So let's say you're actually an energy seller. Let's say you are a solar farm, or let's say you're an EV charging station that has a solar panel on top. You need to calculate based on the weather what my energy output is going to be like. And to do so, you need to use the data and figure out the relationship between the data and the energy output. Excuse me, I had to cough again. And using this data, we are going to predict what your energy output is going to be over I think a 1 week period, and then predict how much energy you can sell. Quick announcement: the exercise exercise sheet has not been published to GitHub yet. After this lecture, we will first publish the exercise on CoCalc along with the exercise sheet within an hour or so. And then followed by this, we will also upload these slides and the video, of course.